all the necessary tools to look at applications of log and exponentials. Applications. It's all about equations, all about what we just did. There are three different types of applications here. One is the exponential growth. Populations grow exponentially. Bacteria grow exponentially. For example, mice, rats, birds, fish, they all grow exponentially. Second application is exponential decay. Exponential decay is typical, it's just more than that, but it's typical for radioactive substances that decrease their mass in time. And here's the last one, logistic growth function or model. You do not logistic growth model. These are three different functions. You do not have to memorize them. They will be given to you. Whatever problem you encounter, those three models will be given to you. They will be stated in the problem. So let's start with the logistic growth model. And let's take a look at 37 on page 530. I'm going to copy the function. This is typical for logistic growth model. 100,000 divided by 1 plus 5,000 e to negative t. Before we even read the problem, let's look at this function. What do you see here? I see a ratio. But this is not a pure rational function because it's combined with something like this, which is an exponential. So first it has a ratio, top and bottom. It's not pure exponential because it has, it's not pure rational because it has an exponential in it. So it's a combo. It's a combination of two functions, rational and exponential. Okay, now let's read the question. So the logistic growth function, f of t, describes the number of people f of t. So I'll take notes. F of t, number of people who have become ill with influenza, t weeks. I take notes. T in weeks. Perfect. After its initial outbreak in a particular community. Okay. Part A. How many people became ill with the flu when the epidemic began? In other words, initially. How many were sick initially? When we say initially, what do we have in mind?
0 weeks.
0 weeks, indeed. Thank you very much. Of course. So we want to find f of 0. So let's try to do this. It's most of the time is impossible. But let's try to do it with 0. How much is e to 0?
0.
Careful. 1. E to 0 is 1. So this is 1. How much is 1 times 5,000?
5,000.
How much is 5,000 plus 1? No, just divide 100,000 by 5,001, and we get the number of people who were ill initially. How much is that? How much is 100,000 divided by 5,001? Oops, I put an extra 0 in there. How much? Part B. How many people were ill by the end of the 4th week? How much did we get?
20.
Okay, approximately 20. So then we're asked find how many people were ill by the end of the 4th week. F of 4 indeed. We cannot do this without a calculator. So let's take a look. 100,000 divided by, don't forget parentheses, 1 plus, bless you, 5,000 e raised to, in parentheses, -4, close the parenthesis, and close again the parenthesis for the denominator. And press enter. So 1,080 people, don't forget the measurement unit. 1,080 people were ill, starting with roughly 20 by the end of the 4th week, 1,080. Part C, what is the limiting size of the population that becomes ill? In other words, as time goes to infinity, f of t will approach what? Exactly, that's true. So let's take a look. Let's say we don't see that. We have the function, let's put the function in y equals, and that is 100,000. Do I have enough zeros? Yes. Divided by 1 plus 5,000 times e, in parentheses, -x, we don't have t, and close the parenthesis for the denominator. So second table. So if I want times 0, this is what I get, approximately 20. If I want 4 weeks, I get 1,080. If I want 25 weeks, if I want 50 weeks, if I want 400 weeks, if I want 1,000 weeks. So how many can they get sick? The maximum is 100,000. That's the size of the city or the population in that.
What was your initial question to that question?
What is the limiting size of the population that becomes ill? So this is the logistic growth model. Let's take a look now. Yes.
You said f of 0, but that was e raised to the minus t, right?
How much is minus 0? How much is plus 0? Still 0. E to 0 is 1. 1 times 5,000 is 5,000. 5,000 plus 1 is 5,001. Is that okay now? Better?
So can I say 1 plus 5,000 multiplied by 1 over e raised to 0? Is it possible? Should you call it that way?
So you want to say that it's 1 plus 5,000 and?
Multiplied by 1 over e raised to 0. Is it correct?
No. By the order of operations, you have to multiply first. You cannot add. So you cannot say 1 plus 5,000 times this. You have to perform the multiplication. And when you're done with multiplying, you can add 1. Order of operations. Multiplication is higher than addition. Higher level. Good. Okay. Next question. Anything else before we look at the exponential growth model?
Question.
Yes, please.
When T90 do infinity, when they have a set number?
No, when it says the limiting size, remember this is the horizontal asymptote. That's the question, actually. It says what is the horizontal asymptote. But since we have not graphed logistic growth functions or models, they cannot really ask what is the horizontal asymptote. They're asking what happens, how many people can get ill in the long run. But if this village or the city has 100,000, assuming nobody comes in to visit, then we'll say the limiting size of the population who can become ill is the size of the city. But I didn't want to say a horizontal asymptote because we really don't know how this function looks like. So that's why I put it in the graphing calculator and I said, okay, let's see what happens. After 4 weeks, after 10 weeks, after 25 weeks, after 400 weeks, and then it's clear it cannot be more than 100,000. So the limiting size, the maximum number of people who can get ill is the entire village. Very good question, actually. Thank you. Is this okay? Okay, very good. Thank you. Okay, so let's take a look at an exponential growth model. And are we interested in, this was the logistic growth model. This was the logistic. I started with the last one, logistic growth model. Okay, so I'll let you decide. Are you interested in the population of Israel or the population of the Palestinians? I can go to the half-life of the radioactive decay just yet. Or we can also talk about New Zealand. There is a situation with New Zealand. Okay, you want the Israelis? Okay. So 7 on page 529. In the year 2000, the population of Israel was approximately 6.04 million. In 2050, it is projected to grow to 10. Use the exponential growth model, and here's the exponential growth model that will be given to you in any problem. A of t is A0 e to RT. Have we seen this before? A equals the principal times e to RT. We've seen this before. It's the same function with the continuously compound interest. But as I said, the model will be given to you. Okay, they're not using R. I wanted to use R just to refresh your memory the same. They're using K. You want to use R or K? It doesn't matter. R is the interest rate. It's the growth rate in this case. Let's use K. K or R, doesn't matter. K it is. Your book uses K for the growth rate and uses R for the interest rate, annual interest rate. Same thing though. Okay, perfect. In which T is the number of years after 2000. So T, number of years after 2000. So the year 2000 represents T equals how many years? Of course, 0 years. Perfect. Okay, so use the model in which T is the number of years after 2000 to find an exponential growth function that models the data. And then in which year will Israel's population be 9 million? Okay. So we are told that in the year 2000, the population is 6.04, and in 2050, it will be 10. What is this? Can anyone say, oh, I think we are given in this problem. What are we given in this problem?
The answer?
No, I'm saying in the year 2000, this amount. In the year 2050, this amount. What are we given? We are given two ordered pairs. Of course, right? So can you tell me the first ordered pair? Exactly. Okay, perfect. What is the other ordered pair? 5, 0, 10. Awesome. Thank you. That's exactly it. Which means when time is 0, A of 0 is, when time is 50, A of 50 is, that's it. We have to put in these two ordered pairs in the function in order to determine what is unknown. What is unknown? Careful. This is the y value, or the function. This is the x value, or time. This is the independent variable. This is a number, which we know. So which variables am I talking about? I'm talking about, exactly. I'm talking about this, which is called initial amount. It was the principal before, right? P. And this is the exponential growth rate. Growth rate. These are the only unknowns we have. The initial value and how fast is it growing per year as a decimal number. Okay, so let's plug this one in. When the amount is 6.04, t is 0. So 6.04 equals the original amount times e to k multiplied by 0. But how much is k times 0?
1.
No.
0.
K times 0 is 0. You're right. You're way ahead of me. That's okay. So k times 0 is 0, but e to 0 is 1. I agree. So then I already found, with absolutely no effort, 6.04 million. So I know that the original size of the population in the study is 6.04. That's it. So this is what I have so far.
I see where you're going.
I know you see. I have no doubt. So far I have a of t equals 6.04 e to k t. But now I have another point that I have not used yet. Can you please tell me how to use that point? And I will use it.
10 equals
Exactly.
6.04
Times e.
K. And,
Awesome. Thank you. You can teach this class for me. Perfect. Now, I must clean it up first. How do I clean this up? Yes, exactly. Of course, I have to clean it up. So I have 10 divided by 6.04 equals e to 50k. What is the variable? Of course, there is only one. K. What do I have to do now after it's completely cleaned up? And this is the only way. Awesome. Thank you. Well done. It's the only function that will bring down what? 50k, indeed. Awesome. Well done. Natural log 10 over 6.04 equals 50k. How much is natural log e? Awesome. Thank you, Stephen. So then I'm done with k. What do I have to do to both sides to get k? No, just divide. Divide by 50. So natural log 10 over 6.04 divided by 50. This is very important now how to plug it in. So please pay attention how to plug this in, and we have to have enough parentheses, to get the correct answer. Ready? Okay. So the top is natural log. So natural log, and in parentheses, the parentheses pop up, 10 divided by 6.04. Close the parenthesis and divide by 50. Since there is only one number, I don't need to put parentheses in the denominator. So 0.0100. When we determine these rates, we have to use 4 decimal digits, and we have to round up in this case, 0.0101. So k is approximately 0.0101. Now we have the entire model. The model is, according to the study, the population in Israel grows at this rate per year, e to 0.0101 t. This we have not been able to determine a model using any of the previous functions, not quadratic, not polynomial, not rational, not absolute value, nothing. This is the only one that works, the exponential function. Now there is part B. In which year will Israel's population be 9 million? Part B. When will the population be exactly 9 million? What do I have? What do I replace? What is given? How?
9 equals
Awesome, of course. This is the population. 9 equals 6.04 e to 0.0101 t. I need to clean it up. That's my first step. How do I clean it up? Both sides by? Not yet. You're right, you're ahead of me. I have to divide by this. I have to clear this first. 9 over 6.04 equals e to 0.0101 t. And only now I can do that. Yes, of course, the only option, because those two sides cannot be presented with the same base. I wish. So I will have to apply what to both sides? Excellent. Any questions, please? So then natural log of 9 over 6.04 equals 0.0101 t. I should write times natural log e. Why I'm not writing it? Exactly, awesome. So then t equals natural log 9 over 6.04 over 0.101. Yes, of course, we have to use the graphing calculator for this.
Year 30 and 20.
So what is approximately what?
39.
39, that's good enough. So years. So in the year 2039, yes? Because t equals 0 was 2000. So in the year 2039, if the model continues to be correct, to be applicable, Israel's population will be reaching 9 million. It makes sense because they said in 2050 it will reach 10 million. So it makes sense. Any questions on the exponential growth model? Any questions on the exponential growth model? Should we look at another problem or should we look at the exponential decay? I have 5 minutes. Say it again.
Another problem.
Another problem like this?
Yeah.
Okay, very good. So let's look at let's look at the population of the Palestinians then. So this is problem 8 on page 529. In the year 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. And by 2050, it is projected to grow to 12. Use the exponential growth model, A of t equals A0 e to kt, in which t is the number of years after 2000, and to find the exponential growth function that models the data. Okay, so let's work on this for 1 minute, and we'll do it together. What will you create? You will create two ordered pairs, and they are 0.3.2 and 50. Very good. So plug them in carefully and tell me what you get. Can anyone give us A0 already? Of course. So then we have A of t equals 3.2 e to kt. And now we have to plug in the second one in order to determine k.
Isn't it 12
Awesome.
equals 3.2
Perfect. Yes?
k 12 50.
Yes, to 50k. Very good. Awesome. What next? Yes, we have to clean it up. 12 divided by 3.2 equals e to 50k. Very good. Well done. And now,
Natural log.
very good. So then natural log of 12 over 3.2 equals,
50K.
very good. Therefore, we have K. And if you give me the number, I'll put it in. Or if you want me to calculate it, I'll calculate it.
I got it. You're way faster than me.
No, I think you're way ahead of me.
0.0264.
0.0264. So now we have the entire model. 3.2 e to 0.0264 t. Final question. In which year will the Palestinian population be 9 million? Very good. Again, I have to clean it up. You became an expert in exponential growth model in 20 minutes. Well done. How much?
39.
Also 39. So in the year 2039, it appears that if the model is still valid, it appears that